स्पीकर नो आई डोंट हैव कैमरा ये भी बंद रखते कैमरा राइट ठीक नहीं है मेरे पास आई हैव इट एंड वॉक करूंगा All right, it's 11. I think we should start. Hello, everyone. Hello, everyone. I hope this is real class, right? Not virtual one. So you can unmute yourself. Feel free to talk. Your camera should be on, right? I should be able to see you and vice versa. And I also see there are few online participants. Welcome to them as well. What I just said applies more to you than these guys. So please keep your cameras on, mics on, and feel free to ask any questions at any stage as we go forward. So there are few disclaimers. I will try to use minimum mathematics as possible, but still convey the message. However, to do justice with the subject, I have already created some Google Colab notebooks where you would be able to find end-to-end codes written, implement them, learn them for yourselves, but I will not be imposing that as an assignment. But you are highly encouraged. In fact, you should be tempted to run those codes after today's lecture. If that is not happening, that means I have not conveyed the excitement that I feel my PhD students feel while doing those kind of things. Okay, so I have my PhD students, postdocs also joining in for lecture, who has been helping me throughout to do various exciting things in space of data, networks, machine learning. And today I'll talk about what we call as tip of the iceberg. It's a huge problem to solve, right? But today, first of all, we should be able to learn what is the problem. We have been learning so many techniques, so many methodologies, so many approaches, so much mathematics, but where to use that? And that's where I would be focusing on that. What are the advances in field of earth system processes, what it means for climate adaptation, resilient engineering. Again, I want discussions to happen. If you are not writing any codes, I would request you to close your laptops. Otherwise, you would not enjoy. I will just end up speaking for 1.5 hours. You will not enjoy that what we are talking about unless absolutely necessary. Please only then use your laptops. Otherwise, let's talk today. Is that okay? All right. And I want participation from everyone. How many of you are civil engineers in this room? Other than my students? How many of you are earth scientists in this room? How many of you are climate scientists in this room? Huh? Activism is fine. All of us are activists, right? So all of us are climate activists in that sense, but somebody who is getting their hands dirty with climate models, climate data. So good thing is that none of us, right? So it's good opportunity for us to learn something new beyond what we already know. How many of you are having background in computer science and engineering? Fantastic, right? So two different poles talking to each other, right? So we should make sense. There's so many words written here: data driven approaches for earth system processes, climate adaptation, and resilient engineering. So what are these? Let's try to make sense today. All of you must have heard this, right? Data is the new oil. We have, why it's said so? Anybody? Feel free to talk on each and every slide, right? I have not added any text other than these 3 or 4 words. I'll get the captions from you. Anyone? Why it is said so? Why data is new oil? What it really means for you as computer science and engineering students? Yeah. Huh? It fuels whatever we do. Okay, one thing. It has great amount of monetary value. What else?
And most decisions today by the organizations are data based. So it's very important to know what is the quality, certainty associated with the data. I think.
Thank you. So quality aspects of data, we have to make decisions. So when we also talk about oil, especially in country where we don't have really huge sources of oil, it's a scarce resource also, right? It has real value associated with it, right? It would be found in scanty, but would be used in plenty. It would be an energy horse for us to drive future innovations. So it makes sense that data is a new oil, and all you might have heard from top persons in the field, including the last talk, right? How they have been using data at the center of various algorithms to develop something meaningful that we do. Unlike various other fields where data is in scanty, we have it in plenty. We means climate scientists are scientists working on various domains of these two areas. We have huge volume of data. In fact, we have more volume of data than we can handle. We are generating more volume of data sometimes than we need, and we can store, and we can process, and we can digest, and we can use for decision making. Right? So the problem here is other way around. We have oil, we have a lot of it. So we are Middle Eastern countries of data actually, when it comes to climate and earth sciences, where we have a lot of oil, right? They have a lot of oil. So we have a lot of data to play with, to process with. So if you look, currently we are in 2020. So in semiconductor world, there is something called as Moore's law. Anybody? What is Moore's law? Can we say something similar for data? Right? So we may have something related to that, that every year data is doubling, and right, and when you plot it, it looks like it's growing exponentially. From where these data sets are coming? You see that we have data coming from models. We'll talk about these models. We have data from satellites. We have data from radars, right? All of you must have heard these terms, right? Satellites, radars, orbiting around us, collecting data and sending us. Be it the precipitation or rainfall that is happening today, there must be some satellite that may be hovering over us, measuring densities and intensities of clouds, densities and intensity of raindrops that are falling from clouds, digitizing it and sending to our repositories that we can later access and make sense of it. Right? So a lot of data coming, new satellites every day in thousands being launched in near orbit, far orbit. So they are generating data. We get access to that data. We have a lot of in situ data. In situ means that you have set a gauge, an observation point where you would be able to collect that data in real time or near real time or after certain interval. For example, if you walk towards our academic block and see on top of block 5, you will see some anemometers rotating, certain gauges placed, which are measuring real-time rainfall that is happening on campus, which is measuring wind speeds as winds are flowing. So that's a classic example of gauge. Why it matters for data scientists, why it matters for civil engineers? Because we need to know from where our data is coming. If we don't know, as somebody rightly said, we need to know the quality of data that is being generated. Otherwise, this data would be useless. That's why I'm emphasizing on it. And together they end up in petabytes. So as of 2022, we are 130 petabytes of data that we have. 1 petabyte, 1000 terabytes. Computers you have in front of you, 2 terabytes. Now you can imagine how much volume of storage we would need to store this data. That's why I said we have a lot of it. We really have a lot of it. But still, most critical pieces of information is missing, and that's what we are going to talk about today. So we typically say that we have 4 V's of data in abundance. One is volume. We have velocity, because the volume is okay, but the rate at which this data is generated, it's also tremendous. We have variety, data sources, as I just spoke about, and veracity. There are a lot of uncertainties in these data sets. You take 5 products talking about same rainfall that is happening over IIT Gandhinagar campus, all of them will have significant differences. Why? Because all of them are making some estimate. It's not like satellite is able to see the exact drop of rainfall that is falling. It is measuring various other aspects that can be used to derive what would be the value of rainfall associated with that particular characteristics of atmosphere. It's not the exact value that it is measuring. So we have derived variables. A lot of variables are derived variables, so which we derive from various algorithms, mathematics that we are going to talk about in some way. But I hope you understand that we are going to going to deal with the problem, which is large scale. We have data, we have oil, but where is the car that we want to drive? What to do with drums and canisters of oil if we don't know what we are going to do with it? So today we are going to figure out that what car we want to drive. So far, you have been talking about so many approaches, so many algorithms, what we also call as hammers in our arsenal, right? You have tools with you now. You have been learning LSTMs, you have been learning, let's do it other way around. Can you name a few topics that you have been learning in this particular session? Don't worry about detailed mathematics. Just give me the topics. What you are learning in this class, what you have learned so far? Yes. Huh? Bayesian. What else? Logistic. Gaussian models.
Yeah, gradient descent method.
So gradient descent is one specific approach that is used to identify optimal set of weights, right? So I would broadly say, to give it more specific, linear regression plus, right? Because it would be used here to estimate the weights. What else?
HMM, hidden Markov model.
Sorry, can you? HMM. Hidden Markov models. What else? Clustering. Fantastic. What else?
We also talked about evaluation of models, how to select the right model. How do we know that model is successful?
Okay. So broadly, what I heard vaguely is some aspects of modeling, right? So we have all these tools where you will apply them. We are running out of applications, right? So what are the problems you would like to solve with them? Okay, air pollution, will again come to that. So in addition to broadly machine learning, including deep learning, we also have suite of data-driven tools like network science. All of you might have heard this word graph theory, right? Where you try to represent things like graphs and do certain mathematical interpretation of the underlying structure that you are getting. And they have also been making their inroads to deep learning algorithms like graphical neural networks and so on. We also have first principle models, right? So you might have learned in your high school physics that if you know mass of the body and you know at what rate it is accelerating, what you can calculate? The force, right? Force that is being exerted on that particular body. It's a classic example of first principle based model. By the way, I have been hearing this word models so many times. What is a model? Before we even go to first principle model, what is a model? Model is a function. Somebody is saying model is a function. So this is important because today all our discussions would be around models. So somebody is saying that model is a function. Anybody else?
Model is a generalization.
We try to simulate the real life happening through model because and use it to predict future.
Simulate and then go towards future. Fantastic. Anybody else? What is a model? So it's a simplified, I would say highly simplified representation of real world, right? We have a complex world surrounding us. We really want to understand because we want to predict, we want to forecast. In some cases, we want to control. We want to create a model. Sometimes we do it physically, right? So before computer science existed, before numerical simulations came into picture, how people will design boats. They will design very small scale prototype before they invest in large ships to understand whether it would be stable, non-stable, and so on. So that's also a model. What is the real product? A ship. What's the model? A small miniaturized version to some scale of that particular entity. Do you think we can also do that for all the computer science or soft computing stuff that we have been reading? It would be very hard because, you know, data has grown in 4Vs tremendously. It would be very difficult for us to do everything in physical space. That's where we use abstract space or mathematical space. You might be learning about those vector notations, right? R to the power D, R to the power M and N, which often you find very confusing when you are reading it for first time. But they take us one step closer to that abstract world where we can try to visualize that how a world will look in mathematical entity. But the most beautiful thing about models are that all models are wrong. But some are useful. Whenever you are dealing with a complex system, all models are going to be wrong, right? But they would be useful to some extent. They would help you understand some aspect of that particular system at macroscopic level, microscopic level, right? And that's the beauty of model. They are not going to tell us exactly what is going to happen day after tomorrow or next day, but they would give us some understanding of the system. They will give us some summary of the system. They will give us long-term behavior of the system. They will help us quantify uncertainties associated with those particular forecasts, predictions that we are dealing with, so that we are not clueless, but we have some idea. One classic example of models that all of us saw was COVID-19 prediction models, right? Every day, a new research group will come with some forecast and will tell that in next 10 days, expect these many cases, these many casualties, and so on. Now, if you look them in hindcast, weren't all of them wrong to some extent, right? Did any model give us exactly precisely same value of every parameter that they were simulating? But were they useless? No, they helped us understand some statistics that where we are heading in best case scenarios, in worst case scenarios. And this applies to all the models that we are going to deal with. So that is one thing that we have to be careful about. Then we have language models also. So somebody used the word activism as I started my lecture, right? Scientists also study activism very precisely, that in what direction sentiments are heading. When certain policies are formulated, how people are reacting or about to react or will react if similar policy come into enforcement, right? How the people have been talking a lot about global warming these days. People have been talking a lot about cutting greenhouse gases emissions to meet our climate goals, right? That would always splutter certain reactions. Some people will be pro, some people will be anti, and policies have to be made keeping both the sides in mind. And that's where these language models come into action, where they help us really understand the sentiments when similar policies come into picture. So now we have tools, and now we are trying to find the application that where kind of problems they will solve. Then we have highly valuable probability and statistics. Whenever we are dealing with forecasts, the best estimate, we are always making an estimate. Those who are familiar with the world of probability and statistics, what is X in probability? Random variable, right? You can express a roll of a dice, a toss of a coin, precipitation outside today, water flowing in the river outside, with a probability. Once you have a probability, you try to express it as a probability distribution. If you are dealing with specific discrete outcomes, you talk about probability mass functions. Otherwise, you talk about probability distribution functions. Once you have PDF, once you have PMF, what you are going to do with them? What you are going to calculate? Expectation. What is expectation? That it's a summary statistic of whatever distribution you have generated, right? You call first expectation as mean, second expectation, right, around mean as variance. Then you go to third, you go to fourth, you go to fifth, you go to skewness, you go to kurtosis, you go to higher orders, right? But there is a purpose for which they are designed. When we talk about this interdisciplinary space, that for you it may be just a mathematical notation, for us it's behavior of the system, where it is inclining, what is the uncertainty around that. And of course variance tells us that this is highly uncertain or less uncertain given what is the spread of that particular distribution. And then finally, some rare or rarely used terminologies would be extreme value statistics. So it is raining since you have arrived on campus. Is that right? Would you be worried about drizzle? If you have, right now it's drizzling outside. If I asked you that, can you go from your place to wherever you are staying? Would you be worried? Why? Because it's a drizzle. You are used to it. Now, if I tell you that it's raining cats and dogs outside, not literal cats and dogs, it's the phrase that we use to tell that rainfall is really heavy, as if cats and dogs are falling on your head. Would you still be comfortable? So as climate scientists, as civil engineers, as earth scientists, sometimes we may not be interested to know what is business as usual outcomes, but we would be specifically interested in rare events. What may happen once in 100 years? What may happen once in 500 years? If you are designing a nuclear power plant, what may happen once in 5,000 years? Once in 10,000 years? Because I cannot afford to lose a nuclear power plant if there is a strong wind in that particular area. And that's where I deal with rarest of rare samples. How many times it rains cats and dogs here? Maybe once in a year, maybe once in 2 years, once in 5 years. So already I had petabytes of data. I had lot of oil, but I really needed special class of product, which is in rare. So I design a specific set of tools that are suitable for those kind of extremes. So there are a lot of hammers in our arsenal. Now we have realized that whatever you are learning in theoretical space has application in some other hyperplane, right? So, but the question is, if we have, yes. Yeah, so I'll talk about that. I'll give very specific examples that as we go forward. That the question is that how do we study extreme value statistics? Because we already, chances are so less, samples would be so finite. So how we would build any distribution, and we'll talk about that, how we do that as we go forward. But right now our question is that when we have hammer in our hand, we always keep on finding for nails, right? That I'll drive this nail in the wall. Arey bhai, I don't need it, but I have a hammer, I will drive it. Do whatever, hang your picture, hang yourself, I don't care. But I have a hammer, let me drive it here, and then we will think about it. But let's do a little bit of step back. And now that you have learned or are learning so many approaches, so many techniques, let's do a little bit of a brainstorming that what we will do once we learn these things. So I will give you 4 minutes or 5 minutes or 6 minutes. Let's make it round figure, 11:30, 11:24, 6 minutes. On your piece of pen and paper that you have with you, and those who are sitting online also, requesting you to think about it. Don't talk to each other. Just think about it. That when you see the world around you in space of climate, environment, engineering, what are the most pertinent problems that you can envision where you can use all those tools that we have learned about to solve specific problems, right? So for example, rainfall can bring flooding, no rainfall can bring droughts, right? Somebody mentioned air pollution. What are the other things that come to your mind when you hear these three words? Environment, engineering, climate, what we want to do with so much data that we have, what kind of models we want to solve. So 5 more minutes, think about it. Bullets are also fine, and I will try to ask as many of you that where they would go. try to come up with at least five bullets, 5 problems that bother you the most when you hear these 3 words. What is this notation, by the way? Anybody can help me? Oh, you cannot see my screen. Okay. What is this notation? Real space. Today we are talking about real space. So that's mathematically real. This is actual real problems that we are going to talk about, right? So, and then we'll relate these two in the next slides. All right, 3 more minutes. Done. Can you give this to me? Can you clear it if it's okay? Yeah, you can write on a fresh page and just so it would be great if you can give me the page that you are writing it on. I would like to read it. So on a small piece of page, wherever you're writing, you can tear it off and give it to me. So those who are watching it from home or online, you can always send me text in chat window. And I would like to see those 5 things that you have thought about here. All right, last 1 minute to wrap up this exercise. So today we will have more generic discussion, right? That is, what is the problem? What are the solution spaces? Tomorrow we'll have a very specific focus session where we will solve one of the problems that we will identify today with help of codes, computers, and everything, right? So you get an end-to-end overview. Okay, how this is how problems are thought, how they are conceptualized, how they are modeled, and how the end products look like. All right. So I also have a few comments online: agricultural soil degradation, extreme weather, trajectory of climate change, estimating impact of policies, real-time climate threat monitoring, weather prediction, focusing on mitigating farming losses, then air quality, then sewage spillage during raining session, and so on. So, and there is serious overlap in all the recommendations I get here, right? So I think I have around 35-ish, 30-ish responses. If you do a text summarization, you would be able to find what are the 6 most frequent words that are given here, right? Mayank Singh must have talked about language models, right? This is what I wanted to also talk about, that this is how you collect samples, right? This is what people will do. There would be a keyword on discussion. People will add so many tweets. We cannot read millions of tweets coming out. So somebody who is expert in NLP will go and do text summarization and would identify what are the 6, 7, 8 most frequently occurring words that describe entire nature of data set, right? So nevertheless, we are going to use certain keywords from here, but one keyword that I see across these is managing natural disasters, right? It includes predicting, forecasting. You cannot manage unless you know where things are going to happen. Some of you mentioned mitigate. Mitigate means stop them from happening. Some of you are saying once they happen, we should be able to help the people who are suffering. We call it as adaptation. You see the difference, mitigation and adaptation. Let's not allowing them happen because you cannot manage them. It's mitigation. When we talk about climate change, when somebody at Paris would talk about climate accords, agreements, they would specifically talk about mitigation. That let's change the way we are developing so that we are not increasing carbon dioxide concentrations or GHGs, greenhouse gases, beyond certain limit. Whereas island nations would be more concerned about adaptation. See, we have already done so much damage to us. We cannot wait to go back, reduce the trajectories. We are already here. Tell us what to do now. Should we build a seawall? Should we leave the island? You might read the case of Kiribati, right? One of the first islands to have climate refugees, where people were forced to leave their home just because of various factors, including sea level change, changes in urbanization pattern, which again was one of the keywords. So that means that some of the problems are already here. Some of the problems may happen. Some of the problems may not happen, but if they occur, the chances or the damages that they will be bringing would be unprecedented. So we have to prepare for different spectrum of problems. So how we do that? We cannot put all the dollars that we have, all the rupees that we have in equity in everywhere, right? Certain problems would need higher prioritization. Certain problems would need little bit less prioritization, depending upon their expectation, probability of occurrence, damages that they will bring, right? And likelihood of occurrence in near future, in intermediate future, in far term. Right? And this is exactly the summary of the responses that are reflected. Many of us are thinking about intermediate or problems that are already there. Sewage problems in city, flooding problems because rainfall is happening outside. Interestingly, I don't see many comments on droughts, but had I been conducting this session in May, many of you would have written when rainfall will occur rather than when rainfall will stop. Right? But as a policymaker, we cannot do that. We cannot afford to do that because we have to look into all possible scenarios that may arise out of such situations. But interestingly, we have few samples here and let's have some conversation. Sanjana. So you have written, we want to use these models. That was the question. You want to use these models to understand changing flow of rivers. how you would design the model. Let's think about that. Let's have a little bit of conversation now rather than me giving a lot of gyan without listening to you. So how you will design this model? What you need as, so what is your background? You are a computer science BTech? BTech. Okay, second year? Huh? Final year. Okay. So you must be knowing this notation at least, that some X and Y, right? So X is what X represents in a typical ML data language, what we can broadly say as predictors, and Y would be our target variable, right? Or predictant. Now we are talking about solving a real problem. We have data. Let us assume we have all the data in the world that you will need. And I will sort of testify that yes, indeed we have data. I think we never talked outside that what you are going to tell me, but I will give you very specific sources of data sets from where you can go download and use them, right? So what you would need to solve that particular problem?
The amount of water.
Huh?
The amount of water the river has.
Okay, so what problem we are solving first?
So trying to.
So you are solving changing flow of rivers,
Yeah.
right? So perhaps that's your target variable.
Yeah.
You need to know values of flow in the river, right? There is a river on my right side. Water is there. You put a gauge, what we call as in situ observations. Satellites may not come handy for such a small discharge. So that means we can go to what we call as a website called as India WRIS, and it will give you discharge data. So that is available. So Y is sorted out. There would be a lot of uncertainties, by the way. None of the data sets I'm going to talk about are perfect, right? But let us take that with pinch of salt, that rather than doing nothing, we have something to begin with. So we will have this data for you. So this is because once you know the time series of flow, you can always measure changes in flow. So that will solve part of the problem. But what is X? You are developing a model. What do you think you would need to predict that change in river flow?
So the terrain. The terrain of the region.
Terrain. We call this terrain as DEM or DTM, what we call as digital elevation maps. So there is a satellite product called as Landsat, which will give us the terrain information, whatever satellite will see from the top, right? By active or passive remote sensing, that is either by sending a wave or by understanding the reflection of particular wave of known frequency and wavelength, we should be able to tell what is getting scattered, and we will be able to generate a digital elevation map of that particular area. So first thing has been given to you. Fantastic. What else you would
So
need?
the distributaries and the tributaries.
You would need what we call as drainage map.
Yeah.
Once you have a DEM, once you have a DTM, you can always identify. So think of DEM as this particular stage. We take earth, bend it to follow curvature of the surface. At each point, we add a number which represents elevation above mean sea level, right? So this grid map becomes an illuminated DJ floor where you can dance now, right? But constraint here is that you can only dance from high value to low value, right? So if I illuminate the values here, so you can visualize what I'm trying to say. All of these grid points are having a number. Let us say deeper points are marked as red, higher points are marked as blue. Constraint is you can only jump from blue to red, going through entire spectrum. So when you do it, you will be following path of a river, right? You start from here. If you follow that particular path, you will reach the ocean, because that would be lowest elevation, 0 meter. You start from all the grid points, all of you will reach the ocean, because it's a natural system. You end up with a drainage pattern. Somebody discovered it back in 1990s that we can really use DEM to identify all the rivers that are flowing on the earth. became first simple model. So you have been thinking in right direction so far. So you have generated your own drainage map coming from DEM. What else?
So rainfall.
Yes,
pattern.
you would need rainfall. Rainfall is also available. So Indian Meteorological Department will give you, satellite products will give you, including Aphrodite, including MODIS, sensors on MODIS would give you precipitation, and various other sources will give you. And these are combinations of model, reanalysis, observations. But we are again thinking in right direction. We are designing a model from scratch, right? So don't underestimate this part. Sometimes we get the tool, we solve the problems, but we never do this model thinking. How people think when they design the model. But now next question arises, precipitation of when? Today? Over what period of time?
About 30 to 40 years.
13 to 14 years, that's fine. We are talking about predicting value of that particular river flow today, tomorrow, day after tomorrow. So let's talk about one specific data point. What happened there? Okay. Yeah.
So time-
Would only data of today will suffice, or should I also include data of yesterday
we should include.
and day before yesterday
That should be considered.
and last Sunday? 2 Sundays before?
So to predict the pattern.
We have
the
to
data.
look into pattern. Am I talking something recurrency here?
Yes, sir.
What language models also do? The next word I'm going to speak depends on the previous word. Last word of the sentence will depend upon from where I started. But next sentence may not depend on the previous sentence that I spoke. In this case, it did. Right? But in next example, previous example would not matter. So one thing is for sure that it is context dependent. I would need T, I need T minus 1, I need T minus 2, and so on. And I will identify the pattern because I don't know where to stop. And that's where these hammers in my arsenal gives me way to do that. I will look into something called as autocorrelations. How things are correlated with themselves. Auto means self, correlation means relation in a linear space. How things are related to themselves. If I see that after 15 days, after 20 days, there is no correlation whatsoever in my target variable and the rainfall, I would say let's not worry about anything T minus 15. But again, a logically chosen step. A logical mind will always take us towards that there has to be a way to either make an assumption or make an informed choice. What else you would need?
Vegetation or flora of that
Vegetation,
place.
excellent. We again have lot of LULC data. These are again satellite products, land use, land classification data set. Land use, land cover, land use, land classification. It tells us where concrete building exists, where green cover exists, where river exists, where snow exists, where patch of land exists. Right? Again, that data is available to us. What else you would need? Think about it. Anybody else can also participate, by the way. This is not an exam, not a viva. Feel free to be part of the discussion. Type of soil, we will also need type of soil. We have soil maps with us which tell us which kind of soil exists where. What else we would need? Huh? Consumption pattern. Okay. So we would need all human factors. Somebody was speaking online.
Sir, population map.
Population maps. So population maps available from survey or what we call as world pop, which gives forecasts of population because census are conducted every 10 years. Population changes with certain patterns. So see the interesting thing. This is what we call as model thinking. We did not start from solution side. We started from the problem side. We started from thinking of all the factors that you think that are necessary, that we combine with the experience, right? I would have somewhat more experience than you in developing these models. That's why I'm talking here. right? So we combined experience with logical thinking, use the data sets that are generated by third party agencies, tell them which data sets don't exist, which we may need in future. But this is the first step that we do in modeling, identify all the ingredients that are available with us for the problem that we want to solve. Then we do certain data exploratory analysis. What are the patterns? What is the cyclicity? What is the stream flow patterns that are there? How much water is actually flowing here? Then we also look into completeness of underlying data sets. We may also see certain features are strongly correlated with each other. So rather than just increasing volume of data without adding any information, what's the point? You are just confusing your model, right? Complexity doesn't necessarily mean it's a beautiful model. Do you agree with me? Have you heard the word support vector decomposition? SVD? What is SVD? Anyone? Huh? Feel free to speak. What is the maximum thing would happen? You would be wrong, right? Nothing else. Feel free to speak. What SVD tries to do? Anyone? Have you heard the word dimensionality reduction? What dimensionality reduction tries to do? Huh? Can you be a little louder? Reduces number of working dimensions. How? Just delete one column that the game we used to play Akkad Bakkad Pampe Bo.
You could use something like PCA.
Principal component analysis.
Yes.
What PCA does in background, identify eigenvalues, corresponding eigenvectors, try to understand which of them are most orthogonal, try to eliminate which are not, which are having lot of information content. So no Akkad Bakkad Pampe Bo, but we have a better mechanism to do that. Right? So what we call this as a data pipeline. See, we are thinking from starting point to end point. So we are making our data point, the entire data pipeline like that. So this particular step is still pre-processing. We are still pre-processing data, doing feature engineering, feature selection. There are two terms, by the way. One is dimensionality reduction. Another one is feature selection. Anyone can tell me difference between these two? So here you have mentioned these 6 features, right? I can also say, let me hypothesize that flow in the river will also depend upon how many students are living in IIT Gandhinagar. It will also depend what kind of breakfast I ate in the morning, right? It will also depend how good T was, a binary variable. Nobody is stopping me, right? All models are supposed to be wrong, right? So it's my will, I will give some wrong variables. Who can stop me? So one example I often give in my data courses is that correlation is not necessarily causation. Number of cars every year are increasing, so is my age. Every year I grow by 1 year, right? It's a normal universe. Number of cars in Ahmedabad grow by 10,000. You can plot my age versus number of cars, it would be around straight line. And then you can say, stop growing. You are increasing number of cars by 10,000. You are contributing to greenhouse gases emission because there is a strong correlation. Yes, I cannot deny there is a correlation. But I will stop you. Say you are confusing correlation with causation. Number of students at IIT Gandhinagar campus may be correlated with river flow, but that is not necessarily the causation. So I have to, and also support vector decomposition may not be able to separate the orthogonality in this particular case, because it may indeed be orthogonal to all other columns that are present here, right? Because indeed taste of the tea may not have any correlation with the DEM. So that's where we do feature selection, either guided by mathematics or guided by domain understanding or guided by the visualization that how a real system would look like that is going to impact my results. So that's where become an important step. But here everything is coming with the cost. What we are talking with so much ease has billions of dollars already invested behind them. Do you think satellite that is collecting LULC was launched for free? Do you think data that we got was processed for free? Do you think data where it is stored after processing it's for free? So there is no free lunch theorem again. Right? But all these things are now coming into action because we have already created that petabytes of archives to be used. But again, most important thing here is the model that we are going to talk about. Now you scribbled so many ideas, apply the same thinking to all the problems that you have listed in your priority list. You should be able to come X and Y structure of your model. Right? If not, that means, let us say you're not able to come up with Y and X, what you will do? This was an easy problem, at least for me, because that's my domain. I work in water. Right, so I chose a problem on water so that I can talk with specifics with you. But some of you may say air pollution, some of you may say sewage collection, some of you may say wastewater treatment, right? That means domain will change there. We would need another domain expert in the room to talk about that. But let us say that even that domain expert says, oh, it is, we don't have X, we don't have Y. What we will do then? Come on, you feel free to speak. This is what you are expected to do, by the way, few years down the lane when you join industry, when you join research, or those who are already practitioners. That's what they do all day, right? What you will do? Yeah, please.
You could model it as a time series problem. So
okay, very good answer.
Take observations.
Treat modeling as a time series exercise, that just take this as intrinsic variable and try to see that how things are related to themselves.
So your X becomes
and try to see whether X at time t is function of X of t minus 1, t minus 2, and so on. What we typically call as autoregressive models, ARMA, RIMA, SARIMA, not GARIMA, right? It stops at SARIMA, NARIMA.
You could also look at using LSTM, say. You can also look at using LSTMs for bidirectional.
Yeah, so LSTMs are also similar construct models where they try to understand. Perhaps here I am talking about all these ARIMA, AR family models. They are typically linear models other than NARIMA, which is non-linear autoregressive integrated moving average model. But yes, that would be the first thing I will also do, that try to understand what data itself is telling. But still, you have missed one nuance here. One nuance is that your X and Y should be very specifically defined. You cannot have vague definition of Y. For example, we started with vague definition. What you wrote was changes in something. Before we even talk about changes, we need absolutes of something. So we made Y more specific. That is observable, that is interpretable, that is recorded, so that we can start constructing a reasonable model. Perfect. Anybody else? So let's say that that model doesn't give us anything. We fail to predict tomorrow's value based on day before yesterday's value. Classic example is our stock market. Nobody knows what is going to happen day after tomorrow. It's all random walk. It may have some noise from yesterday, but you would find serious loss of correlations, even the time series itself. Right? So linear models may not work there. Perhaps that's the nature of the process. It's all noise. I don't know. I'm just saying that that is one example where that particular model will absolutely not work with ease that we are thinking here. What else? We may use unsupervised models, but you have a specific problem that I want to tell the value here. So unsupervised models may tell you the class, category, broad classification, what we typically do in unsupervised clustering, right? Unless you make it little bit supervised, what we call as semi-supervised, it will just tell you I belong to class A, you belong to class B. I don't know what class A is, what class B is. What else? Think as a user. First step in model thinking is to think as a user. What is the first word of my lecture? Title of my lecture? Data. We will see what data is available, what data is missing, what data we need to collect, what would be the closest proxy of that particular data. I gave an example of DEM, digital elevation map. It is just proxy of the surfaces. So imagine a satellite is going, it sees a dense tree cover. What it is going to observe? It is just going to observe surface of the tree. It is not going to observe what is beneath that particular tree. It's just the proxy of an elevation map. And lot of uncertainties just stem from that particular uncertainties that come in that particular model. Right? So we will have to take one step back, collect the data sets that are necessary, find the closest proxies of that data set, make them useful for our consumption, and then again do the same step. But two things again, X has to be specific, Y has to be specific. If you talk to a mathematician, they will say even the hypothesis has to be specific. Even the domain of the problem has to be restricted. Right? That's where R to the power N, R to the power D, or R or C, those kind of spaces come into picture. That whether it's in a real space, it's in a complex space, it's in a universal domain where this problem applies. We are still taking a lot of freedom here. And we are talking in the small r space, that is the real world space, that what is the proxy, what is the approximate solution to this real problem that I have at disposal. Does it make sense? Does it ring a bell that how we can start thinking about a model? But first thing is use inspired. In earth sciences, in climate scientists, in climate sciences, we go behind user inspired solutions rather than the theoretical one. You gave me the usage. I have these use cases with me, right? These are all possible internships, or I'm sure some startups are already working, some companies are already developing products, or some have already developed products in that space waiting for deployment to happen. Some have already been deploying them, but waiting for profitability to happen, waiting for investments to come, right? Some have already been profitable, but that may not be in the user space, but are powering a lot of things that we purchase, insurance, reinsurance, one example of that, right? So that's how the first step, logical step in modeling looks like. So the first case study that we had today is modeling river flows, which we just did through you, right? But I'll give you one very specific example. I said, right, I have a magic wand, whatever you will do, I'll just convert it to slides I am speaking. There is some ML model here, which is doing that in real time, right? So this is what we do. We take the earth, try to imagine what are the various components that come and interact with each other. You see that we have aerosols, we have oceans, we have vegetation, we have urban footprints, we have humans, civilizations, we have terrain from mountains to lands to oceans. This is exactly what you said. And this is how a state of the art, what we call as hydrological models look like. They try to include as many components as possible, try to convert that realism into some numerics so that it becomes X and feeds Y. We can increase complexity as much as we want because somebody said soil. Soil is one part of it that we see, but vertically also things are changing. If soil already has some moisture before rainfall started, it will have less absorbing capacity. That may mean more floods because now absorption is happening. That's what you see puddles right now on campus. Go to our sports field. When it rained on day one, it was pleasant. When it rained on day two, it became muddy. On day three, it became splashy. On day four, it will become flooded. Now, because there is an actual pool of splurge of water resting there. Right. So next advancement of model will try to include that vertical structure. And somebody who is dealing with soil mechanics, soil geotechnics will tell us, okay, this is the values that we observe. This is how this particular soil behave. Again, another domain expert comes into the field. So one thing that we should appreciate that as a computer scientist, you have no luxury to operate alone now. It's an interconnected world. That's why civil engineer is talking to you today. 20 years ago, this might not be the case. Civil engineer would be working in their lab, computer scientists would be working in their lab. But now computer scientists say that, see, we have enough understanding of these things. We have developed LSTMs for you. You have this data where recurrency may be there. Can you please see that how this model will solve a real world problem? And that's where this handshake happens, right? But this is first logical step done absolutely right by you guys, that think logically, think all the processes. But there are few things that we do understand about these physical world. There are few things that we really don't understand. For example, a geotechnical engineer will come, a civil engineer will come and will say, okay, I will take one core and understand the soil structure, how the soil looks like. But he may not be able to dig the ground throughout the volumes. He or she may take few samples, try to understand the distribution, draw inferences from what we observe, but not a full spectrum of distribution. And we try to parameterize these processes. What is parameterization? It is sort of filling the unknown understanding that we have about mechanism. Can you give me one example of parameterization that you see around you? Anyone? We all do parameterizations all day. One example, again, do model thinking. Think about Google Maps. Can you think of what parameterization that happens? Okay, but let's talk even more real world before we go to abstract world. Okay, but that's the process, right? You want to go from A to B, that's the process. What Google Maps do, it will develop a model for you. Model in the sense that it would account for some travel conditions, average speed on which people travel divided by that. Yeah.
Traffic.
Yeah, so traffic is something you may parameterize, right? So you know that on an average, I will be traveling at speed of 45 km per hour. There is 90 km of distance. I should be there in 2 hours. But what your mind will say, I have to cross Ahmedabad city. Let us add 15 minutes there, right? What you have done implicitly, you have parameterized your model, right? You have said y is equal to mx plus c, where m and c are your parameters, and c is a bias or a constant shift that you have added. That see, my model is saying if I travel with this particular c, y is equal to mx. Even m is something you have better understanding, it's the slope basically, but it is also parameters in machine learning discussions. Let's not go there, but you said that let me also adjust for bias that may come into process. So you have filled that lack of understanding based on certain observations, some empirical understanding of the system, and we say that we have parameterized the model, and most of the times we heavily parameterize these models. Soil, we will assume it's same everywhere in the campus. Do you think that's the case? Population distribution, we will assume it's same throughout the campus if you are developing hydrological model of the campus. Do you think it's the same? Right? So one thing is resolution, because we may not have information. Another thing, we may not even have understanding of the process. So we'll just make some empirical observation and we'll nudge the value so that my output is closer to what I am observing. Y is equal to mx plus c. I give you some points on the scatter and I ask you to fit a straight line. What you will do? You will take a straight line. You will keep on rotating until some objective is met. Right? You are also introducing certain parameters on a known structure of a model, and you will estimate m and c based on the observables or y that you already have. But these parameters comes at serious cost. For example, whenever process understanding is poor, when we don't understand what is happening under the soil, we will see serious deviations whenever those components will kick into action. You see, there was a good agreement here, everything is going nice, but then suddenly snow happened and snow was parameterized wrongly in my model. And I will see serious disagreements between my observations and my predictions. And once these kick in, perhaps this may be the most critical time when I needed my model the most. My model is saying, relax, buddy, there is no chance of flooding. And you see outside, every entire basin is flooded. Your model has failed you at the most critical time. right? And this is a real model in action. This is the real model that I set up, ran, calibrated to perfection, was getting absolutely great statistics. But when I looked microscopically, I realized parameterization created a problem. So that was all physics. We thought that if physics is like this, can we really replace certain components with data? Where we understand water will flow from high point to low point, let physics take over. Where we don't know anything about the process, let machine learning take over and do best approximation for us, best estimation for us. Then we simply said, as you rightly said, that I will assume runoff, water in the river, is simply function of what happened at previous day, day before yesterday, 20 days before yesterday. Rather than modeling it as a linear function, I would model it as a non-linear function. Not only that, I will also include other external variables. Right? So there are two variables, exogenous and endogenous variables. Endogenous variables, intrinsic variables that depend on the process themselves. Exogenous that we take from outside. Right? So runoff, intrinsic is runoff T-1, T-2 and so on. Rainfall, external, ET external, information about terrain external, but I am able to convert that into a mathematical function. As I promised, we have created a nice notebook for you, which we will share with you, and you will see all the data sets that you were mentioning in action there. All the data sets downloaded from real sources, tuned to real model in action. Right? And it's a typical LSTM that we have trained with certain lags. And I would encourage you to experiment with that model. It will give you an end-to-end pipeline, how data is obtained, processed, visualized, feature selection happens, LSTM sets up, and how the model training looks like and how the results look like. Even one of my PhD students, Praveen, created that notebook in 1 hour, 1.5 hours, right? But it will give you a full end-to-end pre-processing, training, application, and wrap up that how things really look like. Does it make sense? But it will do what you want it to do as one of the objectives. But we have been hearing this word machine learning, physics, models a lot. Are there any parallels between these two worlds, or they are orthogonal to each other? Both of them we are trying to model. In one case, we try to have more of a process thinking. In machine learning, we would have more of the data / hypothesis thinking. That I have a data, let us see that what is the best I can do with that particular data, even if underlying target is same. Right? Isn't that what many times data scientists do, computer scientists do? That let us not worry about the domain. Let us worry about what data is telling us. And there is nothing wrong, by the way. Somebody working on physics model will assume that only physics is correct. Forget about data. If F is equal to MA, F is equal to MA. I don't know. Even if there is a deviation, something is wrong with data. May be true for such first principle models, but may not be true when a lot of unknowns come into picture. What if your estimate of A itself is wrong? What is estimate of force itself is wrong? That's where machine learning help us fill those incomplete gaps, but there is complete complement that exists here. In one case, we are using all these processes, known equations, known conservation of mass, conservation of energy laws. In another case, we provide these as boundary conditions that I know an objective function. If your estimated mass is more than the system's mass that originally have, your model is wrong, penalize it. Find a new weight, new set of weights that would conform to that physical law. I am bypassing entire process understanding by trusting on the underlying structures. If model is simple, I would know in and out how this is happening, how that grid line is adjusting. But if my model itself is black box, I may have limited understanding of the process. Right? I would assume, yes, I know I can set up a neural network. I can know input space and output space, but I don't really care how that particular weight was learning. I care about that I am able to find a way that this learning was happening. which of course has pros and cons, right? Now you can very well appreciate somebody looking from domain side. I say, this is nonsense. You have created more mass than it was originally there in the system. Your mass is not balanced, your energy is not balanced, will not own this particular model, right? But you would say my predictions are better than yours. He said, I don't care. I care about the physical interpretability. So we are operating in two spaces. One is which is physically more consistent, more interpretable. As she was telling the story, all of us can relate to that, right? Yeah, this makes sense. What variable she's telling, it makes sense because it's a physical world. If I immediately change it, my entire lecture, in Netflix now there is a feature, right? You can choose the next action in which direction story should go. Have you used that feature? If not, today this is the homework. Watch one movie on Netflix where you can do that interaction with the movie, right? Huh? Yeah, Black Mirror was one of them. Now, so there was a guy who keeps on going to jungles, right? Bear Grylls, Discovery. So he has created 3 or 4 shows where you can decide the action. So he would be holding a snail and then 3 options will come. Swallow it, chew it, throw it. Then you can choose the action, what you want that person to do, depending upon how much tolerance you have for that violence, right? But you can direct the story accordingly. So similarly, let's revise that discussion. Instead of choosing data and physics, she clicked on data. So I'll say, I have some variables. I have Y. Let's not talk between. I will fit a model, right, of 10th order, 12th order, 13th order, having lot of non-linearities inbuilt, using ReLU, using leaky ReLU, somewhere using sigmoid, and here is the model. Which one makes more sense? First one, because it is more intuitive. It resonates with our physical understanding. Which one may be better? The second one, because I can train the model to death. Here, a lot of inconsistencies already in assumed model structure may come into action. So that's how these things have certain trade-offs. No perfect world exists, unfortunately. And that's where we started looking into that. What are the complementaries these two worlds, handshake of civil engineer with data scientists, offer? It gives us greater bandwidth to explore the range of functions that we have. So if you see that center red dot, right, it represents how much choice of physics we have. How many laws of motion you have studied in physics? Newton's के थे ना law of motion? 3, 4th नहीं था, 5th, 6th, 7th, 8th. So we are left with small dot. How many architectures of a neural network you can design? Infinite, right? You have choice over hidden layers. You have choice over units in that hidden layer, activation units. You have choice over what activation function you are using. You have not only neural network, you have choice over different hammers that we introduce in our arsenal. That I don't want to use neural network, give me simple regression model, give me support vector regression. So this gives us interesting bandwidth to explore, right? I will use these equations. These are 11 equations that I know. I will complement them that certain equations are more fundamental. For example, if you look at equation number 4, it is a simple that W is equal to S plus P. Right? Let us say that W is total water. It is sum of water that is present above the ground and below the ground. You don't need machine learning to do that. Do you? It's as simple as that. Hai na? If we ask how many bottles are there in the class, you will not need a machine learning model. You just count the water bottle. That's it. So we said, let's take best of that particular world. But if you see equation number 5, doesn't look very fundamental equation, right? Looks like somebody has observed these things once and put some squares and square roots to fit the values. And he assumed, he or she, whoever developed this model, assumed that this will generalize to all the possible cases. Isn't it bad? Isn't it something we can improve now, where we have a lot of data, lot of understanding of machine learning models? change intrinsic structures while making sure that E4 also holds true? Doesn't it make sense now if we think from that particular perspective? Right? So we are now again doing handshakes of the both worlds so that we can exploit the full function space, and that's where these data driven approaches again come handy. One very specific example, this is from the same notebook that we have designed. This is the mathematics that go behind that notebook. I promised I'll not talk much about mathematics because I've already encoded that for you in the notebooks. But this is what that particular notebook is exactly doing. It is exploring that functional space. It's saying that I want Qt. Qt is my target variable, flow in the river. Initially, I was saying there are 7 equations on the variables that you gave me, that this is how variable looks like. Let's put the value, we'll get an answer. We have lost flexibility there. We may have to parameterize certain things, but we lost the flexibility. Here you are saying, I just care about the function. Be it linear, non-linear, I don't care. I know machine learning, I know data science. I'll just find this particular equation. LSTMs may be one method. You may use something else, but this is what it will give us. Right? And now what we did in our lab, we said, let's combine both of these. Let's combine best of these both worlds. People were talking about physics. People were talking about machine learning. We replaced certain data boxes with machine learning. We surrogated machine learning into physics architecture. At the end, my mass is balanced. At the end, my energy is balanced. At the end, processes where I had least confidence, I left machine learning to do them. At the places where I really wanted physics to follow, I let my physics-based model to do that. And this is one case where we have really deployed this particular model in action. And I think we applied it to how many basins, Praveen? 7? 10 basins of India to show that this really has a value. Because now physics gives me interpretability. Machine learning gives me predictability. Best of both worlds give me something which is interpretable as well as predictable. Next thing we talk about, you mentioned extreme precipitation. Somebody said floods. What you would do with floods, by the way? What is flood? Anyone? Feel free to speak. This is the class where we should discuss rather than preach. What is flood? Excess water. If overflow happens, very good. Any other definition of flood? Last bench. I love last benchers because I used to sit in last bench every time I have attended some such classes. So I know how hard the life is there. Yes. What is flood?
When the water gets above the sea level and we are not able to manage that water.
Okay. So anything that breaches certain level of normalcy, not necessarily it has to get out of the river. Even if flow is in excess, we call it as a flood.
Unregulated. Like
Sorry, somebody is speaking online. Please go ahead.
unregulated.
Yeah, unregulated flow, flood of information, flood of tweets, flood of water. Right. But interesting thing about flood is that for me, flood is temporal phenomena because I am looking into time series. For Google, it was spatial phenomena. So Google has been developing an interesting engine where they are using machine learning in space to tell us or design an early warning system for flooding. And this is taken from the blogs that Google has published on their website, I think last year, that it will tell us that as the flood propagates, what is going to be water level rise, what is the percentage change in the flooded area, and if you are at that particular place, how much of submergence will happen. Again, not a perfect model. None of the models are perfect. We really also don't know what is under the hood of this particular model. So somebody coming from domain, I would still accept this with a pinch of salt unless I really see whether it's a physics or that AI or just data into action without having realism of physics. right? Because I just see a blog article, I'll get fascinated for 1 hour, but then I will see what is the underlying set of equations, variables that are used to set up this particular model. And that's exactly what we were doing in model thinking. But one thing is for sure that it is now finding applications in flood and AI, but this is the starting point that how these models are conceptualized. If you see that particular figure there, it's a typical combination of DEM, LULC, vegetation, and soil. Now look that figure closely. Do you see some green patches, brown patches there? Do you see some deep trenches, some highlands there? Right? And do you see certain pixels marked there? What those pixels are? What they are doing at that particular point? Why they have green dots there? So they are collecting samples. To set up their machine learning model, they need X and Y. What are the X's and Y is inundation or not? You can also set it up as regression model. For these particular X, what is the level of inundation? How they will do that? They will do some sampling from dry patches. They will do some sampling from wet patches, or permanent water, non-permanent water, and so on, and try to tell us holistically that how we can combine this data to come up with an answer. And this is just the starting point, by the way. We are still very, very far away from what we need. All this may be sounding very fascinating, oh, everything is solved. No, this is just the starting point, tip of an iceberg, right? 2020, still a lot of validation to be done, still understanding whether data sets that are used to create these maps are credible, how they are performing in real urban areas. Somebody mentioned sewage in urban areas. Flooding in urban areas may not be caused by rainfall. It may be caused by aftermath of rainfall, when all your sewage systems are full and they backsplash, because our infrastructure may not be designed or clogged or not ready to take that particular rainfall. So it's just a starting point of this fascinating areas where problems need to be solved. If you were wondering we are all doing it in social cause, you are wrong. Now big techs are also stepping in to solve these problems that we need to solve for future. So as I said, it's a problem in space, it's a problem in time. For us, it's a spatio-temporal problem. If river, even if it is not crossing the banks, but if it is flowing in full velocity, for me, it's a flood. Why? Because it may damage the dam structures. It may render river unfit for somebody who depends on their livelihoods for fisheries. It may still put villagers who go to river every day to fetch some drinking water. Still, it's a flood, right? You are not supposed to go near the water because things are in excess. That's where I would need to know changes in discharge. But if I really want to understand whether I would be able to drive today to Ahmedabad or not, I need that spatial map, that where is exactly the location of flooding from where I cannot drive. So as I said, this is one typical example how ML has been used for flood detection, where we get these satellite images, set up a classification problem. Cat and dog problems are typically told in classical courses in machine learning. But again, we are repurposing those models to solve the problems of today. So towards the end, I'll just talk about, we have understood there is a flood. We have understood that our systems are at risk. We have understood that we, to a certain extent, can predict where flooding will happen, where damage will happen, where is the probability of occurrence by using these models. What do you do with them? Is machine learning solution for all the problems? Is data science's solution for all the problems? Of course not. None of the models are perfect. None of the models are 100% going to solve a problem like a magic wand, right? But they are useful to some extent, and we go beyond just what we understand in machine learning AI space to first identify the problem and solve them. So for example, we said that now we have understood something about flooding. Flooding will occur here, there. What it means for my nation, what it means for my city, what it means for my region, how we lose connectivity. As soon as word connection comes, the first word I think of is graph. When the word graph comes, I think of graph theory. When I think of graph theory, I realize I'm not a computer scientist. So how can I talk about graph theory? Then I realize there is something called as empirical graphs, what we call as networks. So we go to the doors of network science, try to use the mathematics of graphs, apply it to model real world systems, and try to understand them as graphs, not as a purist, but as somebody who's applying these particular topics. And again, these are the snippets from our work where I mined the data set. This was my work that I did during PhD when I was doing PhD. Again, it was a problem driven thinking, not the solution driven thinking. I have a hammer, let me find a nail. But I said, there is a problem that we need to solve. How we'll go about that? Data was scarce. This was the place where data is really an oil. We don't have enough of it. It's very expensive or sometimes difficult to connect. Right. So I will not name that ticketing website because I'm on record, but we mined their entire website to find from which station they were issuing the web tickets, to what stations trains are going, at what places trains were stopping. Once we did that, they changed their data sharing policies. Now we cannot do that. But that gave us a way to map the entire nation's railway system as Indian Railways network. Now this, what you see as a fancy thing, it's just a geocoded version of messy graphs that you see. It's a complex network representation of the same graph. We just shifted each node to their exact geographical location and we ended with the representation of India. But it's a mathematical entity. It's not a real system. It's the model of a real system. A lot of imperfections, right? Because typically we were able to have more confidence in origining and destinating stations, but less information about intermediate stations. But again, a model that enabled us to gain some insights. And what we realized that people have been doing these modelings for ages, but people have not been looking into from what it means for large scale infrastructure systems. What if events like flooding, tsunami happens to our nation and how these systems are going to respond? Even if we understand the response, what to do next? In minutes, in seconds, somebody takes control of our cybersecurity systems, bring our 20 station to the knees. How you are going to recover from? How you are going to prioritize? Again, mathematics help us. We set up our objective functions that let us restore those particular stations where our gain is maximum. Gain could be number of passengers able to board the train. Gains could be revenue that railways will generate. Gains could be number of people around that particular station who would benefit if that particular station is back online. And again, it's a classic example of a data-driven model, right? And we end up with these particular representations of the system. And then we complement what we understand from flooding with graph theories or representations in network space and try to understand how our local regional system will behave when these flooding events strike our systems. Yes. Yes, people have been also using that as an anomaly detection. And again, a lot of applications also exist there. But again, we need to know an underlying data functionality that at how we are defining anomaly with respect to the known functionalities. But here we have bare bones basically, right? We would not know how many number of trains are cancelled or how many trains are operating. We would only know the underlying structure and try to impose the hazards and disasters that we have been talking about. And then recently, in fact, this was the last year where we connected all the dots. We said, bring the hazards, bring the networks, give us a real system. We will identify what happened during that particular event, which we missed capturing just by paraphrase of news. We applied that to understand our Kerala floods of 2015. Anybody coming from that region would relate, not 2015, sorry. This was 2019. Though anybody coming from that region would know that what havoc floods, landslides play in that area every year. So we brought best of all the worlds, quote unquote, best of all the worlds, because whatever best we have that particular stage in terms of methods, getting information on floods, getting information on where infrastructure was disrupted, where landslides were happening. Right now we understood how to do flood mapping using remote sensing products. We knew how to use networks to understand which roads were operating and which roads were not operating. We knew physics of certain processes, right? And we combined all of them. Again, we'll not worry about that. But here, if you see, this is the data box that I have been mentioning, data and using various layers of data that we observe, combined with our understanding of physics. and obtain the functional time series, that at what point we were going anomalously below the intended functionalities. And we identified that we were underestimating our risks by more than 70%. See, that camera has also gone anomalous, right? So we were underestimating our risks by 70%, right? And again, these are starting points. Lot needs to be done, but there is serious possibility to translate whatever we are talking into some serious products. I started with climate adaptation and resilience. What we mean by resilience is that systems are going to go down. Doesn't matter how much you prepare. You cannot make risk zero, right? Risk can never be made zero, even if you know everything about the system, everything about the hazard, because it would entail investments. So we started developing these resilience data-driven products where we said that an informed choice can save us millions of dollars in terms of extra revenue that we would generate if we know which point to restore, which point to manage, which point to strengthen, and bring back online in the wake of these particular hazards. So not only that, I mean, these are some of the glimpses that whenever we develop these frameworks that clearly show that there is a serious appetite in nation across the globe, right? We really lack multiple solutions that immediately these things are out. Media, for example, immediately identify that, oh, this is what we need to do, right? And then, of course, this is still a starting point, I would say, of this fascinating world. We have learned about a lot today. We'll continue our discussions next time, but let us end up this talk with that data is indeed a new oil and we have a lot of it, but we don't know what to do with it entirely. That we are still trying to decipher. In tomorrow's class, we'll talk about one very specific, very interesting application, because we have an activist with us, climate activist, right? So we have not spoken about future climate. We have only talked about what is going to happen, has happened, how systems respond. But first, now, next organic question should be, what is going to happen tomorrow? How do we know that? Can machine learning help us? So tomorrow we'll talk about that. I hope you enjoyed it. And tomorrow we'll have one lecture and one lab session. So looking forward.
Hello,
Thank you.
sir. There is a question from audience. If you can take a look at it.
Sure.
In YouTube.
In?
YouTube.
Can you read that question?
Yes,
for me?
yes.
Yeah.
There must be some involvement of calculus in this field, right? So they're asking, like, fraction calculus is helping us to find much accurate solutions than integral order calculus. Can you suggest some, if there is some scope of fractional calculus in this field?
So I may not be best positioned to answer this question at this particular stage, but I'll definitely get back on more specifics. Perhaps I did not understand the question well, Sark, but we should note this question and answer in the next class immediately. Yeah. Any other question? Sark, please definitely note down the question. Let's answer after thinking it thoroughly. All right. Thank you.